1 hour on this planet is 7 years on Earth, and a flight into this black hole is a wild ride through space and time. The movie Interstellar is a real sci-fi masterpiece that still fascinates me today. We'll find out if this planet, time travel, and the black hole Gargantua could really exist. It's gonna be super galactic. Welcome, friends. Christopher Nolan's Interstellar has raised the bar for scientifically based science fiction films. If you are as fascinated by the connection between science and fiction as I am, then subscribe to the channel right now. Subscribing is completely free, you will never miss an exciting video again, and you will help me immensely. Thank you guys. Drop me a line and tell me which is your favorite science fiction movie. I'm in desperate need of new movie recommendations, and I'm very curious. For me, it's definitely Interstellar. With its depictions of wormholes, black holes, and time dilation, this movie caused a sensation and was so good that it is still being analyzed today. But how accurate are the depictions really? And what about the scientific basis of other popular sci-fi franchises? Today we'll be taking a look at one of the most famous icons of science fiction films and clarifying how scientifically accurate it all is. Be sure to stay tuned until the end, because then we'll be talking, and this is no joke, about the scientific aspect of ALF. I'm really looking forward to that. But let's start with a detailed analysis of Interstellar and find out if we can really travel through space and time like that. Interstellar managed to depict the topic of time travel more accurately than any other movie. Renowned scientists such as wormhole researcher Kip Thorne helped write the script, and the movie clearly shows that the intention was to stay relatively close to the scientific facts. That's why Interstellar is my favorite science fiction movie. The movie is about the following, and I don't think I have to have any scruples about spoiling a 10-year-old movie. The Earth is no longer really habitable for some ominous reason, and humanity has to find a new planet to survive. The protagonist Cooper and his daughter perceive very mysterious signals in their house, which appear as if by magic, and tell them, among other things, the coordinates of NASA headquarters. The two of them drive there, and Cooper is quickly drafted into a space mission to save humanity because a wormhole has conveniently appeared in the solar system, leading to a relatively promising system. There are a few planets there that could potentially be habitable. The catch is that the planets are moving around a black hole that goes by the beautiful name of Gargantua. In the end, Cooper manages to travel back to our solar system through this very black hole, but many years into the future. It turns out that it was he who was able to communicate with his daughter in the past through the gravitational curvature of the black hole. So he was the one who caused the mysterious signals in the house that led the two of them to NASA in the first place. Let's start with the black hole system. Is that realistic? A system in which there is no star but a black hole, and in which planets orbit stably around that black hole without being swallowed up? Absolutely, because there is a big misunderstanding about black holes. Many people see them as the voracious monsters of space, but they are actually just totally misunderstood. In reality, black holes just need a little love. It's all good. In a certain range, black holes have a gravitational force that is strong enough to form an event horizon, i.e. a boundary beyond which not even the speed of light is sufficient to escape the gravitational pull. As a rule, black holes are also very, very heavy, as one might imagine from the cliche. For example, the black hole Sagittarius A Oriz at the center of our galaxy has 4.3 million solar masses. The heaviest known black hole, Ton 618, weighs in at 66 billion solar masses, but theoretically, superlight black holes are also conceivable. You could even say that anything can become a black hole, even me. An object only has to be compressed to such an extent that gravity forms an event horizon in a certain area. The lighter the object, the more it would have to be compressed. For example, if you wanted to turn the sun into a black hole, you would have to squeeze it to 3 kilometers. The Earth would have to be compressed to 8.7 millimeters, so a black hole does not have to be extremely heavy, and it does not have to suck everything in. The effect of the gravity of a black hole works exactly the same as with all other celestial bodies. Take our sun, for example, which holds the Earth in its grip through its gravity, but it does not suck the Earth in. That would be dramatic, just as little as the Earth does the moon. Only if you were to get too close to the sun would you be pulled towards its surface by gravity, and it's the same with black holes. Only if you get too close will you move towards the center and eventually cross the event horizon. The only difference between normal celestial bodies and black holes is that the gravity in a certain area is so strong that light can no longer escape. And that means it is perfectly conceivable that planets in a system could form a stable orbit around a black hole. And there is now an official term for such planets: planets, a portmanteau of black hole and planet. Interstellar was even ahead of science because the term planet did not even exist when the movie was made. So far, no planets have been discovered in our galaxy, but I am confident that this will soon change because it is even relatively likely that planets will form around a black hole. The accretion disk that orbits many black holes, a huge collection of gas and solid matter, contains enough material for planets to form. And even if such a planet had a fixed orbit around a black hole, that doesn't mean that the strong gravitational force would not make itself felt. And that brings us to the second major theme of interstellar time travel. When the crew lands on one of the planets called Miller's Planet, which orbits Gargantua, they experience the relativity of time firsthand. 1 hour on Miller's Planet is equivalent to 7 years on Earth. It is exactly the same effect that you experience when relatives force you to listen to an hour of stories from your crazy uncle.
What a name right now. But what we just saw, we just left pleasure. Paradise. For paradise.
The crew received the signal to land on the planet from Dr. Miller, who had located the planet. Actually, years before the film's plot. But when the crew lands there, they find fragments of Miller's spaceship that look as if they were still brand new. The crew realizes that if Miller landed 21 Earth years ago, it was only 3 hours ago on this planet. And after the crew of Miller's Planet flies back to their spaceship, which is waiting at a distance from the planet, they realize that only a few hours have passed for them, but 23 years on Earth. Cooper's daughter is now older than he is. All this sounds completely unbelievable, but it is scientifically accurate. Albert Einstein already found out that space and time are inextricably linked. An extreme mass, such as that of Gargantua, not only bends space, but also time. Under this massive gravitational influence, time passes very differently on Miller's Planet than on Earth, which is not exposed to such an influence. It is difficult for us to imagine because we cannot see time, but it does not change the fact that it is present everywhere as a dimension, even here. Perhaps it is easiest to imagine as a trampoline that is pushed down by a heavy weight. If you take this idea a step further, it gets really crazy. There could be alien civilizations that have developed on planets, and for whom only a few days have passed, while we have been tinkering with our civilization for thousands of years. I would like to address another interesting aspect that is rarely mentioned: the strange behavior of the water on Miller's Planet. The planet seems to be covered by an ocean, but the water is only knee-high. At first glance, that doesn't sound too bad for the perfect next summer vacation. However, there are also gigantic tidal waves which could somewhat spoil the vacation experience. The depiction of the ocean on Miller's Planet is also scientifically very accurate. Miller's Planet is shaped like a football, one end of which is constantly pointing towards Gargantua. It orbits Gargantua with a fixed rotation, always showing the black hole the same side, just like our moon, which also always presents the same side to the Earth. And the waves on Miller's Planet are actually not moving at all and are coming towards the viewer, but rather it is the planet itself that is rotating under the viewer, and the waves are fixed and then eventually break. And these fixed waves, which are created by the bound rotation, also explain the otherwise knee-high water, because a large part of the planet's water is permanently bound in these waves which do not dissolve, and that's why the rest of the planet is only covered with shallow water. In many videos, this aspect is not sufficiently appreciated, I think, because this is the only correct representation I know of in a movie of a gravitationally bound water planet around a black hole. Okay, that doesn't happen in that many movies either. We have now established that the existence of planets with gigantic tidal waves is basically possible, but let's take a closer look at the physics of Miller's Planet. One of the main reasons why Miller's Planet is not swallowed up by Gargantua despite its proximity to it is that Gargantua is a rapidly rotating black hole, and the physics of rotating black holes is different from that of non-rotating ones. The sheer speed of Gargantua's rotation means that there is a single stable orbit just outside the event horizon. But here's the curious thing. According to Kip Thorne, the scientist who co-wrote the script, Miller's Planet orbits Gargantua every 1.7 hours for an outside observer. For observers on Miller's Planet, this means that due to the relativity of time, the planet orbits Gargantua 10 times per second, which is actually faster than the speed of light. However, since Gargantua's rotation causes space to be flung around the black hole in a similar way to a whirlwind, Miller's Planet does not travel faster than the speed of light in relation to space, since the laws of physics state that you cannot travel faster than the speed of light in relation to space. But space itself is not bound by the speed limit, and therefore it is possible to travel faster than the speed of light by de facto bending and twisting space as a reference point. Ingenious. I don't want to say that this scenario depicted in the movie is particularly likely, but it is absolutely in line with the laws of physics. But I don't want to just heap praise on the movie. We can also take a look at what is not so scientifically accurate in the movie Interstellar. There is the representation of the sky on Miller's planet. Gargantua is nowhere to be seen, and with the described physical properties and especially the proximity of Miller's planet to the black hole, Gargantua would actually have to fill half the sky. Okay, that's just a minor point and a bit of nitpicking at a very high level. From a scientific point of view, the depiction of the events as soon as Cooper crosses the event horizon of the black hole is more worthy of criticism. He survives and, thanks to the black hole's space-time curvature, can interact with what he sees as the past on Earth and ends up back in our solar system in one piece. So if you ever see a black hole, I would strongly advise you not to try to imitate it, because there is very probably no way to return to it in accordance with the laws of physics once you have crossed the event horizon. The event horizon is the boundary beyond which the gravitational force is so strong that not even light can escape. Since there is nothing faster than the speed of light, the chances of escape would be rather slim. In addition, the tidal forces, i.e. the interaction of the rotation around the black hole and the massive gravitational force, would lead to the so-called spaghettification effect at the latest in the area of the event horizon. Cooper and his spaceship would have to be stretched out and become a cosmic spaghetti. On the other hand, no one has ever been anywhere near a black hole, let alone beyond the event horizon, so we can't know exactly what happens there, and there are some researchers who think it's possible that black holes are connected to white holes, which act as a kind of opposite. While no force of physics can escape from behind the event horizon of a black hole, no force of physics could overcome the event horizon of a white hole from the outside, so you couldn't get in. And there could possibly be a connection between black and white holes. Everything that goes into a black hole is catapulted out of a white hole somewhere else in the cosmos. That would be an Einstein-Rosen bridge, also known as a wormhole. So even that is not impossible, and even though the part of the movie that shows the inside of the black hole is a bit on the edge of what is physically possible, I think that artistic license is perfectly legitimate here, since nobody knows what happens beyond the event horizon. Isn't it fascinating how close Interstellar is to reality? But now we're going to jump even further, to a galaxy far, far away. Star Wars, with its lightsaber duels and the force powers of the Jedi and Sith, is rightly considered the most famous sci-fi franchise of all time. But how realistic are the force lightning bolts of the Sith? Could something like that exist in our reality? Let's find out. Have you ever heard of the tragedy of Darth Plagueis the Wise? No? I thought so. It's not the kind of story a Jedi would tell, it's a Sith legend, and anyone who has ever studied the Dark Lords of the Sith knows that most of them can use the Force to shoot deadly bolts of lightning from their hands. It would be handy if that were possible in real life too. If your coffee has gone cold, you could just heat it up again quickly with a few Force lightning bolts. Ah, perfect. First of all, the explanation provided in the Star Wars movie for any Force activity can be directly discarded from a scientific point of view because it's explained there as follows. No matter whether Jedi and Sith lift heavy objects with the Force, perform mind tricks, etc., the midichlorians are always responsible, tiny life forms that are found in most living beings. The higher the density of midichlorians, the more Force sensitive an individual is. I took a look in my blood for you, and lo and behold, no midichlorians. This could mean that I am either extremely unforce sensitive, or that there are no midichlorians outside a galaxy far, far away. Too bad. But how can we still get our Force lightning? We have to delve deep into the secrets of the dark side of the Force, also known as electrical engineering. Could air conduct the Force lightning at all? If that were to be denied, Palpatine's attacks would fail because his Force lightning would lack a conductor. In fact, air is not a particularly good conductor, but rather a good insulator. Electrical charges are therefore poorly conducted by air, but Palpatine's Force lightning is something else and can therefore overcome the insulating properties of air. In principle, almost everything has a so-called breakdown voltage, which is simply the amount of electrical charge that must be reached for a body to become a conductor. A nice mnemonic device in electrical engineering: with enough electricity, everything becomes a conductor. And you also know this breakdown voltage from everyday life, albeit on a smaller scale. Every time you get a small electric shock, for example on the escalator, or when you rub a balloon on your hair, this is the effect. Here in the planetarium we have an object that you can get an electric shock from, particularly often a plasma ball. I'm just trying to catch one. Awa. What just happened here? My body surface had a more negative charge than the plasma ball, and this imbalance between negative and positive charges wants to be equalized. If it is strong enough, this equalization can take place through a small electrical charge, even though the bad conductor air was between me and the plasma ball. If the imbalance of the charge is large enough, we reach the breakdown voltage. And if I can do that with my plasma ball, it's a piece of cake for a powerful Sith Lord like Palpatine. On the other hand, Palpatine's Force lightning is a little more powerful than my little electric shock. So how could he do it? The magic word is electron avalanche. To understand this, we have to go to the atomic level. When Palpatine shoots electricity from his fingers, he hurls a whole bunch of electrons into the air, negatively charged elementary particles. These electrons hit atoms, and when electrons hit atoms, they can ionize them, i.e. energize them. During ionization, electrons are torn out of an atom, and when an atom loses a negatively charged electron, it becomes a positively charged ion. It sounds complicated, but you all know the effect of ionization, for example, from the aurora borealis. The upper layers of the Earth's atmosphere are ionized by high-energy solar radiation and then begin to glow in the most beautiful colors. By the way, our plasma ball, which maliciously gave me an electric shock, is a nice example of ionization. The ball contains certain gases, and these are ionized when the power is switched on. When you touch the ball, the discharge inside the lamp is distorted. And when an electron avalanche occurs, we have an amplifying effect of this ionization. More and more electrons are torn out of atoms and hit more and more new atoms, which they ionize, until finally an avalanche of ionization occurs and the Jedi scum is completely roasted. Oh, sorry, my negative emotions got the better of me.
Let the heat flow through you.
So far, we are still within the realms of science. If power flashes can be created by ionization and the triggering of electron avalanches, then this must mean that the Sith can control the electrons around them at will in order to create charge imbalances. In other words, they can create the same state that occurs during a thunderstorm, a charge imbalance between negatively charged cloud layers and positively charged areas below the clouds, which is then neutralized by a lightning bolt. Okay, I'm not going to get hit by lightning again. And how do you control individual electrons with pure willpower so that you can fire off a voltage equalization in the form of a power bolt at any time? That's where science leaves us, I'm afraid. It can only be explained by the Force. Apparently, Palpatine has to make his midi-chlorians work very hard to make this possible. Which brings us to another question. If Palpatine apparently uses his own physical energy to manipulate electrons, where does he get this energy from? After all, the midi-chlorians are in his body. Surely you have heard of the law of conservation of the energy. It states that in a closed, frictionless system, the total energy always remains the same. If Palpatine releases extreme energy through his lightning bolts, he must somehow generate this energy in his body, because as far as we know, Jedi and Sith do not use external devices for their Force abilities, but only their bodies. And the energy source for our body is, that's right, food. Finally, a good transition to eat something in one of my videos. How much and what would Palpatine have to eat to get enough energy for his dark manipulation of electrons? Let's assume that Palpatine's Force lightning is comparable to an average lightning strike on Earth. It wouldn't even take that much to kill a human, but for a Sith Lord it should be easy to keep up with an ordinary lightning strike. The basic unit of electrical current is the ampere, and an average lightning bolt comes along with about 30,000 amperes. Converted into joules, the unit of energy, that would be 500 megajoules. Now we can easily calculate how much food you would have to eat for that, because joules can be converted into calories. Palpatine would have to eat so many calories in the Death Star canteen that he would reach 500 megajoules. A Big Mac, the most important unit of measurement in mathematics, contains 500 kilocalories, or 500,000 calories. You always have to be a bit careful with this, because people often talk about calories when they mean kilocalories. Let's do the math. Palpatine would have to eat about 240 Big Macs for breakfast to fire a lightning bolt at Luke that would be equivalent to the intensity of an average bolt of lightning in a thunderstorm. 240 Big Macs is actually doable, so I couldn't do it in a day, but within a week, easy. Palpatine would certainly not be able to convert the entire calorie content of a Big Mac 1-to-1 for the Force lightning bolt. He also needs energy for his other bodily functions, so he should probably eat a few more Big Macs than 240. And once again, science has provided us with fundamental insights into our lives. If you want to hurl Force lightning, you just have to eat a lot of burgers and somehow manage to control electrons in order to trigger ionization through electron avalanches. Long live science! From the power of the Sith, we now come to one of the most iconic alien species in film history. The Xenomorphs from the Alien series are true survivors with a biology that is as fascinating as it is creepy. To these aliens, especially their acid spitting, Work from a scientific point of view? Let's dive into the world of these nasty aliens. You wouldn't want to meet a xenomorph at night. The nasty alien monsters from the Alien series are deadly hunters, use their victims as hosts for their eggs, have a toothed jaw and acidic blood. But would that be biologically possible at all? Could there really be a species somewhere in the vastness of the universe whose blood is so corrosive? In the 1979 movie Alien, we see in one scene how xenomorph blood not only eats through the crew's work boots, but also directly through the floor of the spaceship. We can therefore conclude that the blood must be so acidic that it can even eat through hard materials such as metal. First, a little basic chemistry. You're probably familiar with the terms acids, bases, and pH. The pH value describes the acidic or basic character of an aqueous solution. In a narrower sense, acids are all chemical compounds that are able to transfer protons, i.e. positively charged elementary particles, to a reaction partner such as water. Bases, on the other hand, are all chemical compounds that are able to form hydroxide ions, i.e. negatively charged particles, and thus neutralize acids. Acids lower the pH of a liquid, bases increase it. Even if you failed your chemistry test, you will immediately realize that the xenomorph blood must be acidic rather than basic. A liquid with a pH value of 7 is neutral. Human blood consists almost entirely of water and therefore has a pH value of 7.3, which is pleasantly neutral. Fortunately, you can't attack people with your own blood. Well, you could, but it wouldn't do you much good, except for some very strange looks from passers-by and a criminal charge. If the pH of your blood moves even slightly towards the acidic end of the spectrum, this is a serious condition called acidosis, so there's no chance of you becoming a xenomorph. For other species, it's a different story. Some reptiles change the pH of their blood depending on the temperature and can even survive a blood pH of 6. That is a very acidic pH, but even a pH of 6 is far from the melting through the ceiling of the spaceship level. What is one of the most corrosive acids we know of? Hydrofluoric acid, also known as hydrogen fluoride, can etch through materials such as glass or ceramics. When it comes into contact with the skin, the effect can be so devastating that it doesn't even hurt because the nerves are immediately destroyed and can no longer send pain signals. Even a small amount can be fatal. Hydrofluoric acid has a pH of around 2, which is highly dangerous, but would not be enough to melt a spaceship. So we need something even more corrosive. And here it is, hexafluoroantimonic acid. Even the name is really corrosive to pronounce. Hexafluoroantimonic acid is considered a superacid, and its pH value is so high that it doesn't even fit on the scale. It is a whopping minus 31.3. Wow, that's corrosive. This stuff is so corrosive, the technical term for corrosive, that it could probably eat through the metal floors of a spaceship, albeit a little slower than the xenomorph blood. So far so good, so let's assume that hexafluorantimon acid flows through the veins of a xenomorph. However, it is completely undiluted because if it comes into contact with water, there would be an explosion. What material would the body, veins and arteries of the xenomorph have to be made of so that the superacid blood does not destroy its own body? There are materials that do not react with acids. This is known as acid resistance. You are sure to know one of them, polytetrafluoroethylene. Oh wait, nobody knows it by that name. In everyday language, it is called Teflon. Surfaces that come into contact with hydrofluoric acid are therefore made of this plastic. So today we have learned that the representation of the xenomorph blood could be realistic. It's just that these are creatures whose bodies contain the most deadly superacid and whose bodies are made of Teflon, which is completely logical. But if such creatures really exist on a distant exoplanet, I hope we never make first contact. And I almost forgot, a material that is even more indestructible than Teflon, and that could of course be used to build the alien bodies, is old Nokia cell phones. Now it's getting deep. Few films have challenged our understanding of reality as much as the Matrix trilogy. Let's just forget about the fourth part for now. The idea that our entire world could be just a computer simulation has long since become something that recognized scientists are dealing with. Is this perhaps all just fake? All computer code? In the movies, the basic premise is that what we perceive as the normal world is just a computer simulation, the Matrix, that is feigned to humans by machines. In reality, humans lie unconscious and dreaming in a dystopian reality in which they are abused by the machines as a source of energy. Some people manage to see through this deception and fight against the rule of the machines both in the Matrix and in reality outside the Matrix. The path out of the Matrix begins for the main character Neo in a famous scene with the decision to take a pill, the blue or the red. Only the red pill allows him to escape from the Matrix, but it also means that he has to give up all the comforts of his simulated life. Could it really be like that? Are we perhaps living in the Matrix? Now, many of you are probably saying, totally unrealistic. My life is not determined by machines. Oh wait, I got a notification on my iPad. Gotta take a quick look. The Swedish philosopher Nick Bostrom has been dealing with the Matrix for a long time and calls the whole thing simulation theory. He says one thing that later generations with their super powerful computers could do is to carry out detailed simulations of their ancestors or of people who are similar to their ancestors. If this were the case, it could be argued that it would be reasonable to think that we are more likely to be the simulated minds than the original biological minds. So if we don't think we're currently living in a computer simulation, we're not entitled to think that our descendants will perform such simulations of their ancestors. Ask yourselves, do you think that in 1,000, 2,000, or even 10,000 years, humanity will be so advanced that it could simulate something like this with a computer? I think it's very likely, and if you assume that humans will be able to create a matrix like this at some point, then it's relatively likely that we already exist in such a simulation, isn't it? Because you have to keep in mind that the chances of living in a matrix are purely mathematically much higher than in reality, because there is only one reality, but simulations of reality are possible an infinite number of times as soon as it is technically possible to create them. So you could assume that there are an infinite number of simulations but only one real reality. From a purely probabilistic point of view, it is then clear where we are right now, namely in a simulation. To add a little more to your existential crisis, let's take a look at what Elon Musk says about it. A few years ago he said, if you basically assume further development, computer games will eventually become indistinguishable from reality. We are most likely in a simulation. What exactly does he mean by that? When I was a kid, computer games looked like this. Super Mario, who could run from left to right and consisted of a few pixels, was absolute high-end graphics, and it wasn't that long ago that I was a little boy. And in those few years, computer games have evolved to an incredible extent. Today, games with the latest graphics can almost keep up with the real world. Of course, the technical possibilities to simulate our complete reality in a computer game are still lacking, but if computer games continue to develop, there's little doubt that in a few centuries or even millennia, games can be programmed in which the characters have consciousness. So a bit like The Sims, except that the Sims are really sentient beings and will suffer from your bad decisions for them. In other words, the immense technical progress of computer game development could be an indication that we ourselves live in such a game. So Super Mario World was perhaps just one of the first steps into the Matrix, and here comes yet another argument in favor of the simulation theory, the laws of nature. Clever people can calculate exactly how gravity works depending on the mass of a celestial body and how fast light propagates in a vacuum and so on and so forth. But why are the laws of nature exactly as they are? So why, for example, is the speed of light the maximum speed? Why does the mass of the Earth produce exactly the gravity it does? Why do atoms have their specific properties? Perhaps the laws of nature are the programming code of our reality. Super Mario can only jump as high as the programmers allow him to, and light can only move as fast as the code of our simulation allows. These were all indications that reality could possibly be simulated, but of course no hard evidence. I myself would not put my hand in the fire for it, that this is real, nor for the fact that we are simulated. I would say that I'm completely agnostic about it. I would like to mention one more development that reminds me particularly of the Matrix theme, the metaverse. Companies like Facebook, whose parent company has even renamed itself Meta, want to shift a large part of our lives into virtual reality, into the metaverse. In this metaverse, you should be able to live digitally, attend meetings with a digital avatar, meet friends, and above all, acquire digital property. The topic of digital property is super topical and also goes by the buzzword Web 3.0. While the initial internet, the Web 1.0, allowed users to consume third-party content, from the Web 2.0 onwards, people were able to create content themselves as bloggers or in social media. And now with the Web 3.0, there is also an ownership component. I can not only read or write content, I can also own purely digital content such as non-fungible tokens, or NFT for short, which are basically digital content that has been immortalized on a blockchain and thus become a unique digital item. For example, I could immortalize this video on a blockchain and then sell it at a high price as an NFC. I think I'll do that. To cut a long story short, Metaverse and Web 3.0 are nothing more than steps towards a matrix. If at some point I go to work with my avatar in the metaverse, have to greet Mark Zuckerberg every day, and my house exists purely digitally on a blockchain, then in principle I am living in a matrix, aren't I? And if reality here is already a simulation, then that would be a matrix within a matrix, maybe within yet another matrix, which in turn exists in another matrix, which is also only part of a matrix. Don't get me wrong, I don't necessarily want to present this as completely bad, because I find the developments in the area of Web 3.0 and around NFT extremely exciting. Feel free to write me your opinion about the metaverse and Web 3.0. Is this basically an exciting development, and in which direction should it go? I would be very interested to hear your opinion. To conclude our journey through the sci-fi film landscape, we take a brief detour into lighter realms. Do you remember Alf, the furry alien from the 80s? I love this series and actually still watch it often today. Alf's origin from the planet Melmac was never shown in detail, but there are some fascinating facts about it. Let's travel to Alf's home planet. He is probably the most lovable alien in television history. Alf. In 102 episodes, we learn a lot about the life of the Tanner family's cat-loving Alf, but time and again, Alf also talks about life on his home planet Melmac. In this video, I have compiled 5 fascinating facts about this planet for you so much in advance. Melmac really seems to be a wacky world because not only its shape is a bit strange. Fact 1, Melmac exploded. According to Alf, his homeworld looked relatively similar to Earth, even if the planet was somewhat misshapen. There is only one picture of Melmac that shows its 2 moons. In the year 1985 of the Earth calendar, Melmac unfortunately exploded. How this explosion occurred is highly controversial. While some assume that a nuclear war was responsible, Alf claims that it was because all the inhabitants accidentally turned on their hair dryers at the same time. Fact 2, Melmac was made of Melmac. According to Alf, Melmac was not made of earth and water, but of Melmac. Unfortunately, it is not known exactly what this substance is. We only know that the sky was green and the grass was blue on Melmac. Melmac also orbited a purple star. However, the peculiarities of the substance Melmac may be responsible for the curious deformation of the planet. Fact 3, Melmac had many strange laws. The inhabitants lived in a society with a lot of strange laws. Alf mentions some of them over time. For example, on Melmac, it was forbidden to dance with the postman. One of the most common crimes on Melmac was to tickle your barber. It was also forbidden to wave to a halibut. Laws are important for a functioning society. Fact 4, Melmac was inhabited by strange species. The species to which Alf also belonged were not the only creatures on Melmac. Before that, huge dinosaurs ruled the planet. However, these cannot be compared to dinosaurs on Earth because they were a mixture of dinosaurs and insurance agents, so-called salesman dinosaurs. Furthermore, Melmac was once infested with living loaves. These were created when a baker used radioactive yeast. Fortunately, the living breads were defeated. Fact 5, the calendar of Melmac resembled that of Earth. Melmac takes 386 days to orbit around its purple star. Like on Earth, the year was divided into 12 months, which had the following names: Harble, Tarble, Goroth, Kilmerl, Oring, Barp, Twangle, Fanfan, Nathanganga, Anerva, and Fibble. For example, Alf's birthday is on the 28th of Nathanganga. There are various holidays throughout the year. For example, National Martians Bashing Day, which celebrates the counterattack by mean cucumbers on Mars. So, all in all, you could say that Melmac is a pretty unique planet in our galaxy. Do you know any other fun facts from the Alf series? Then feel free to write them in the comments. I hope you are now absolute sci-fi experts. Of course, there are many more exciting science fiction series that could be analyzed, and if you don't want to miss the next video about it, leave a subscription right now. Let's change the subject and travel to California. Most sci-fi movies come from Hollywood, but this time it's about an earthquake. The San Andreas Fault is awakening, and scientists are very concerned. In the worst-case scenario, San Francisco and Los Angeles could experience a catastrophe. You can find out exactly what we have to expect, and above all, when in the video shown. Otherwise, I'd say, see you in the next video. Take care, friends.